Atomic pudding, we are going to talk about how we came to the theory of atoms that we did today. We're going to go through some of the major developments and major experiments and talk about how and why the model of the atom has changed to the current day model. So by the end of this, we should understand the different models of the atom, understand the development of the Thompson and Rutherford models. Specifically, those are very important ones, and be able to explain the results of those two experiments. We should be able to identify models based on a description, and also we should be able to put the models in order of time, in order of how they came out. That's what chronological order means. I don't know if you guys have heard that term before. Have you? Chronological? Okay. So that's what that means, in order of time. So moving on, Dalton's theory. What I want you to don't have to come do the time frame, but write down that where he came up. That this is the main point about Dalton's atomic theory. Yep, just the second one. He said that there was a tiniest piece of matter. And you couldn't break down matter any more than that. So what John Dalton, basically, to make an analogy, John Dalton kind of viewed, say you guys, who played with Legos here? Have we talked about this? Did we talk about Legos yet? Okay. So imagine that a substance is a constructed thing of Legos. How much can you deconstruct those things? You can deconstruct it until you get to the Lego. And that is the building block of your structure. So he kind of envisioned atoms like that. You can break down matter up until that point where you can't break matter down anymore. And each individual Lego, Connor, is an atom. That's what he made the analogy like. Does that make sense, guys? So imagine you have a structure made of Legos. You can take those individual Legos apart, but each individual Lego can't be broken down any further. Okay? So he called each type of Lego, or each type of atom, he called those elements. That's what he defined. Each element was defined by its size. So that's like each individual Lego, each different type of Lego, was a different element. So this is only partially true in terms of mass. Okay, so I'll let you guys comment. Dalton's model of the atom was just a solid sphere, and his model couldn't be divided up into smaller pieces in a chemical reaction. So in a chemical reaction, you can't break things down any further than the atom. J.J. Thompson. Thompson was a physicist, and he came up with the. He was studying cathode rays. Now, you guys may actually be familiar with a cathode ray tube. A cathode ray tube. Remember how old TVs, they had that big long back?
Is that a monitor?
I don't know if I think the monitor might be a little different, but I know the old TVs.
CRT, yeah, cathode.
Oh yeah, CRT, cathode ray tubes. So what they did is the cathode ray tubes, they projected a color onto the screen, and that's why you had to have this long back to your TV. Now the new LEDs and the new plasma TVs are totally different in how they make their screen. But what Thompson did was he studied the cathode ray. And he found that if you guys look at this bottom here, that when the cathode ray tube was put in a magnetic field or an electric field, that the cathode ray was bent towards the positive plate. So what do you think it means? If it's attracted to a positive plate, what does the ray's charge have to be? Negative. So that's where they came up with the idea of a negatively charged particle in an atom. Now, what do we call that? The negative charge one? Anyone remember? The electron. The electron. So this is where they first came up with the idea of the electron. So the cathode ray was a beam of electrons, they later found out, and they figured that they must have a negative charge. So Thompson's model, he discovered the electron. So don't take this down. I'll tell you guys what's important. So they called it the plum pudding model of an atom. And this is where we came up with the idea that the atom had different parts. So they have an atom part and an electron part. So he kind of envisioned the atom to be like, I call it the chocolate chip cookie model. So if you could imagine the cookie part, imagine your chocolate chip cookie, guys, right now. Imagine it in your brain. I'm sorry to do that before lunch. But chocolate chip cookie. The chocolate chips were like the electrons. And the cookie part was the positive background. So that's what he envisioned them like. Very tiny, tiny chocolate chip cookies. Okay? So, but he knew that the atoms could be removed based on the cathode ray tube when you shove the charge through there. So, Thompson's big things were that he proved that atoms have little negative particles. But what J.J. Thompson did was he proved that elements can be made to emit electrons. And he found that all atoms have these. Nope, don't copy this down. He figured out that there was no charge on an atom. So there must be a positive part. But he didn't really know what that was. And we're going to talk about that right now as we go talk about more Thompson model. Did I double the slide? Yep. Sorry. Until we got to the Rutherford model. He studied physics in Thompson's lab. And don't write this down. And he found out that these particles were sometimes deflected in the air. He had these things called alpha particles, which we'll talk about in a couple days more about them. But when you shot a beam through air, that sometimes they'd be deflected. And he came up with the gold foil experiment. So if right now you guys could just write Ernest Rutherford and the gold foil experiment. The gold foil experiment, Rutherford put some uranium in a lead block. And uranium is a radioactive material that releases these alpha particles. So what he expected to happen was he expected the alpha particles to pass through it. Don't write this down. Because he thought that the atom was like the chocolate chip cookie. So if you could imagine, Raina, can you just look up there? Thank you. If you could imagine like a chocolate chip cookie, and he imagined it was like a bullet passing through a chocolate chip cookie. That's what he envisioned. He thought that it would just be able to pass it because it wasn't a dense part of the atom. So he expected it just to go through the gold foil. So the gold foil is very, very thin, of just a few atoms thick. So he just thought that it would pass right through it because the alpha particles were being shot towards there. What he got was some of them did pass through, but some of them were deflected. Some of them were deflected a lot. Some of them even shot right back at him. He was shocked at this. He said it was kind of like if you what his own example was. He said it was kind of like if you shot a bullet at a piece of paper and the bullet bounced back at you. It's one strong piece of paper. So what he really figured out was that not all of the positive part of the atom was distributed evenly. There was a part of the atom that was very dense part of the atom, which held most of the mass. Anyone know what we call that part? Okay? The nucleus, yes. Very different from the nucleus of a cell. Very different. The nucleus of an atom is very, very tiny. If you could imagine Bowditch Field, the whole, or Foxborough Stadium, big football stadium, the nucleus of the atom would be like a quarter on the 50-yard line. Okay, and the nucleus of a cell would be like the whole state of Massachusetts compared to that. So they're very different size-wise. Okay, so don't get confused with that. I know it's a similar term, but they mean very different things. The nucleus of an atom is very different from the nucleus of a cell. Nucleus of a cell is made of very, very many atoms. Lots and lots of atoms. Okay? Is that clear? So what he found was that the alpha particles were the ones that hit the nucleus were bouncing back and being deflected. So that's where we came up with the nuclear model of the atom. And that, I do want you to take this down. Rutherford came up with the idea of the nucleus. The main part of the Rutherford atom was that most of the atom was just empty space, and that there was a very small nucleus in there where most of the mass is. In fact, we assume that all of the mass of the atom is in the nucleus because the mass of the electrons is what we call negligible. There's not enough mass to affect the overall mass. It's kind of like if you're on a scale, if you imagine you're weighing yourself, and then you take a hair off. The hair has mass, but you can't measure that difference. Doesn't matter. No pun intended. Moving forward, Niels Bohr. And if you guys would take down the name Niels Bohr in the second bullet point right here. What Niels Bohr did, he came up with the idea of the atom that you guys probably talked most about in 8th grade physical science. So he had the idea that the atoms were like orbiting around the nucleus. The electrons were orbiting around the nucleus. So that's where you guys talked about, like, the first shell can hold 2 electrons, second shell can have 8, third shell can have 8, fourth shell can have 32, etc., etc. Does that sound familiar at all? You guys may have done that? Yeah. So that's his idea of the atom. I'm not going to get into the experiments that led him to believe this, but they call it the planetary model. Like, the nucleus is the sun, and the electrons are the planets orbiting around the sun in a fixed orbit. Later, we find that's not necessarily true. Here's a little picture of the Bohr model. So the nucleus in the middle and the electrons going around in orbit. And that's like the traditional one that was around for a while. But later, we talked about, there's another diagram of it, the quantum mechanical model. Bohr and Einstein, you may have heard of that guy. He was pretty smart. He came up with the idea, and don't copy this down. Write the name quantum mechanical model. He had the idea that the electrons weren't necessarily in a fixed orbit, but they were in orbitals. And I'm going to give you an analogy where I'm an electron. So if you guys are looking for Mr. Kilgore, where am I most likely to be found? Right in B108. Am I always in B108? No. I teach a class in C116, so I might be there. I might also be in the office, the science office upstairs, or the main office downstairs. I might be in the teacher's room having lunch. So I'm not necessarily confined to this room. Sometimes I feel like I am. But my most probable location in the school, if you're looking for me, is right here. So what we call that would be my orbital. My orbital would be B108. I'm most probably found here, but I could be other places. And that's kind of like an electron. We call their most likely location, we call those orbitals. The modern view of the atom is that the atom's mostly empty space, and it's kind of like summation of all the different things that we talked about, there are two regions. The nucleus, which has the protons and the neutrons, and the electron cloud, or the orbitals, where the electrons are probably found. So that's it for the modern view of the atom. So I'm going to sum up the atoms right here so we can take a look at them. So we have the old model, which is the Dalton model, which there are just solid spheres. That's it, indivisible. The plum pudding model, which we had the positive background and the negative electrons in there. Or the chocolate chip cookie model. I like that. When I'm a famous chemist in the future, people will talk about the Kilgore model, and they'll call it the chocolate chip cookie model. Probably not. Then there was Rutherford's model, which is the nuclear model, Bohr model, which is the planetary model, and the modern quantum mechanical charge cloud model. You guys don't have to copy this down. I have, if you want to, you can, or if you want to go back later. I've summed up this in your printed notes, if you guys want to take a look at it. I believe this entire chart is there, so you guys can feel free to take a look at that. And it kind of makes sense. They're designed as to how much information there is and how specific the model is, and that's the order of it. So the Dalton model, which was just a solid sphere, is less complicated than the Thompson model. The Rutherford model is more organized. You have your positive nucleus and your electrons. The Bohr model has your positive nucleus with your electrons in orbit, and the quantum mechanical model is just the most complicated of them all, even though it looks a little less. But that's it. Just take a look at our objectives again. We should understand these models. We should talk about and be able to reason the development of Thompson and Rutherford models, the chocolate chip cookie model and the nuclear model. If you got a description, you could be able to look back and tell me what model you're referring to. We should be able to put them in order of time and be able to explain those results of the Thompson and Rutherford experiments. And we are done, guys.